All right, so today we're going to look at a titration curve of a strong base going into a weak acid, and we're going to calculate the pH of the solution along various points of the titration. So we're starting here with 25 milliliters of 0.2 molar acetic acid, and the pKa is 4.75 for that. And we're titrating it with 0.2 molar solution sodium hydroxide. So we're asked to find the pH before we add any hydroxide, after 5 milliliters, 12.5 milliliters, 25 milliliters, and 26 milliliters. Okay, so the first one is going to be an equilibrium problem. So we recall that the Ka is equal to 10 raised to the opposite of pKa. So to find the Ka of the acetic acid, it's going to be 10 raised to the negative 4.75. And this is going to be 1.77 times 10 to the negative fifth. Now we can set up our equilibrium expression here with our products on top. Now we're going to show those as X because we have hydronium and acetate as our products, and they're going to be in equal concentrations. So that's going to be X squared over, we have a 0.2 molar solution minus X. Now, because the Ka of acetic acid is so small, it's less than 1 times 10 to the negative fourth, we're able to use the approximation method. So we don't actually need to worry about this X in the bottom here, which is a good thing because that means we don't have to solve the quadratic. So now we need to find X, which is going to be the concentration of hydronium, which then we can find the pH. So the first step is going to be to multiply this 0.2 out, and then after that we can take the square root of it. So 1.77 times 10 raised to the negative fifth times 0.2 is going to be equal to 3.54 times 10 to the negative sixth, and that's going to be equal to X squared. So the next step is just going to be take the square root of both sides, and that is going to give us X being equal to 0.00188, which is also equal to the concentration of hydronium. So now to find the pH, we're going to use this equation. pH is equal to the opposite of log of the concentration of H+. So if we take the opposite of log of 1.88 times 10 to the negative third, which is what this number is right here, we're going to find that we have a pH of 2.72. And that is our answer for part A. B, now we're adding 5 milliliters of NaOH. So the first step here is going to be to find out the number of moles or millimoles of sodium hydroxide. So we have 5 milliliters of sodium hydroxide, and the concentration is 0.2 molar. If we multiply this together, we're going to find out that we're going to have 1 millimole, and this is going to end up being the conjugate base, which would be acetate in this case. Now, the reason for this is because sodium hydroxide is a strong base, which means it's going to react 100% with the acetic acid until it's gone, and the product is going to be acetate, which is just a deprotonated form of acetic acid. So therefore, the number of moles of NaOH is going to directly correspond to the number of moles of acetate now. So now that we have that, we can use this equation. pH is equal to the pKa plus the log of the concentration of the conjugate base over the acid. So what that's going to look like for us is pH is equal to 4.75 plus the log of 1 millimole, and that's going to be acetate. And now the bottom is going to be, we need to find out how many millimoles we had of that. So we had 25 milliliters, and it's 0.2 molar, which is going to equal 5 millimoles of HA. So for the bottom here, we're going to put 5 minus 1, because we started with 5 millimoles of acetic acid, and we're taking 1 away because we added strong base to it. So essentially this is going to be the pH is equal to 4.75 plus the log of 0.25, because it's going to be 1 over 4. And what does that come out to be? That comes out to be 4.15. So the pH for part B is 4.15. Okay, so C. Now we're adding 12.5 milliliters of sodium hydroxide to it. So first let's find out the number of millimoles that is. So we got 12.5 milliliters times 0.2 moles, which is going to be equal to 2.5 millimoles of acetate, or sodium hydroxide, which will lead to the production of acetate, 1-to-1 ratio. And we know previously that we had 5 millimoles of acetic acid to begin with. So now we can put pH is equal to 4.75 plus the log of 2.5 over 5 minus 2.5, which is 2.5, which 2.5 divided by 2.5 is 1. And the log of 1 is 0, which means that this entire part of the equation goes away here because it's equal to 0, cancels out. So in this particular case, our pH is going to be equal to our pKa, which is 4.75. And that is the answer to part C. So part D is going to be the most complicated part, because here we've titrated to the equivalence point. So there's several extra steps we're going to have to do in this case, because we see that since we had the same concentration of each of the solutions, and now we have the same volume, that means that all of the acetic acid has been used up by sodium hydroxide, which means we're going to be left with just acetate, which means we're going to be looking for the reverse reaction now. So originally we were looking at HA is going to form A minus plus H plus. This is what we were solving for in the beginning with our very first in part A, our equilibrium expression, which we're going to have to use again here. But now it's changed. Now we're actually going to be looking for this reaction going this way, which means we need to find the KB. So if you remember, the Ka times the Kb is equal to Kw, which is the autoionization constant of water. This is a constant. Kw is equal to 1 times 10 to the negative 14th. So we can solve for Kb by rewriting this equation over here and taking Kw and dividing it by Ka. So Kw divided by Ka is equal to Kb, which is equal to 1 times 10 to the negative 14th, and our Ka that we figured out previously is 1.77 times 10 to the negative 5th. And if we divide that, we're going to have 5.65 times 10 to the negative 10, which is really small. So this is the Kb, and this is the equilibrium constant, or the equilibrium expression, that is explaining the reverse reaction here. So now that we have that, we can set up our equilibrium expression. So 5.65 times 10 to the negative 10th is going to be equal to Now we're going to have, again, x squared on the top, and on the bottom now we need to find what our new concentration is. So we know that we have 5 millimoles of acetate now, and we can find that out by taking 25 milliliters and multiplying that by the 0.2 molar, and that ended up being 5 millimoles of NaOH. The NaOH has gone on to produce to 100% acetate. So this is the millimoles of acetate we have. But now we have a different concentration because we have a new volume. We started with 25 milliliters, we added 25 milliliters, which means we now have 50 milliliters. So to find our new concentration, we are going to divide the number of millimoles by the number of milliliters, which will give us 0.1 molar. The milli here cancels out and you're left with moles per liter. So our bottom here is going to be 0.1 molar minus X, but because KB is really, really small in this case, we're able to ignore this minus X. So what we're going to do now is we're just going to follow the steps we did in part A. Is we're going to multiply this out, and multiplying any number by 0.1 is the same as dividing it by 10, which is, so this would be 5.65 times 10 to the negative 11th now is equal to x squared. And now we can take the square root of both sides, and what that gives us, it's going to give us the concentration of OH. So the square root of 5.65 times 10 to the negative 11th is going to be 7.5 times 10 to the negative 6th is equal to x. So now we can solve to find the pH, we need to use the opposite of log of concentration of hydronium, but this is going to be the concentration of hydroxide in this case. So there's two ways we can go about finding the concentration of hydronium. One, we can divide the water ionization constant by the concentration of OH, and that will give us the concentration of H+. Or we can just do pH is equal to 14 minus POH, which POH is the opposite of log of the concentration of hydroxide. So if we do this, we're going to find that the pH is going to be 8.8. And that is going to be the answer for part D. Part E is easy. So 25 milliliters of NaOH has gone into the solution so far and used up all the acetic acid, which means there's going to be 1 milliliter of 0.2 molar NaOH left. So because it's a strong base, we're just going to use the POH to find the pH in this case. So we know that 25 milliliters of the NaOH has already gone and is gone in the reaction. It doesn't exist anymore. So we're left with 1 milliliter. So what we need to do here is find the millimoles, which is going to be 1 milliliter, because that's what's going to be left, times 0.2 molar, and that's just going to be 0.2, 1 times 0.2. But now I have to divide it by a new volume, and then volume is going to be 51 milliliters. And this is millimoles on the top. So 0.2 divided by 51 is equal to 3.9 times 10 to the negative third. So now we can use this equation. pH is equal to 14 minus pOH, which is going to be the opposite of log of the concentration of sodium hydroxide, which will in this case be 3.9 times 10 to the negative third, which comes out to be 11.59. And that is how we solve for the various points in a titration curve.